and welcome to the 9th lecture. So today so what we have done so far, what we have done so far is on pipelining. We've completed pipelining, the basics of pipelining in the last class. We will now continue and we will talk about memory management in the next couple of lectures. We'll try and cover some part of some important parts of memory management. As I told you, the entire computer organization, the development of the CPU essentially is governed by the user. The user directly does not come in touch with the hardware. The user basically gets in touch with the hardware through either the compiler in the form of a compiled code or through the operating system, wherein he requests some services and these services are basically provided by the hardware. So all that we try and study are basically motivated by some user requirement at some point of time that basically gets reflected in the development of the hardware. So today's CPU, the speed, the sort of facilities that the CPU offers, the type of instructions the CPU executes, all these things are basically driven by the user either through a compiler or through an operating system need. So now we will talk about memory management, and when we address memory management, we will classify each that we talk of either as a requirement from the compiler or from the requirement from or a requirement from the operating system side. It is very important for us to understand why certain facilities are available in the CPU. How it is made and what is done is covered in many of the textbooks, but somehow some textbooks, most of them, fail to teach you why certain things are done. And let us go and answer this why, because that is very important for us to appreciate computer organization in a larger perspective. Now let us look at why memory management is very important. Memory management is important for the simple reason that if you take the 5 stages of execution, the stage number 1 you go and fetch an instruction, the stage number 3 you go and fetch data, and stage number 5 you write back data. Now for fetching the instruction is always done from the memory. Many times we fetch data from the memory, many times we also write back results into memory. So at least the 3 stages of the 5-stage pipeline has something to do with memory. Number 2, so point number 1, 3 of the 5 stages touch memory. Point number 2 is when we compare the speed of the memory versus the speed of the processor, always the memory over years have been at least 1 order of magnitude slower than the processor, 1 or 2 orders of magnitude. So since the memory is slow, now we are trying to make a match between a very, very fast consumer and a very slow producer, vice versa. So there is a memory which provides you the instruction and data, the CPU consumes this and probably sometimes also write backs into the memory, but that interface is such that on one end we have a very, very slow device, on the other end we have a very fast device. So we have to make this matching proper. So in essence, the CPU should not be slowed down because of the slow performance of the memory. As the memory is slow, and since this requires data and instructions from the CPU, from the memory, the CPU should not also become slow because of the memory performance. And that is one very important aspect. So lot of innovations, lot of new additions to your CPU architecture has actually become today as a reality because of the speed mismatch between the memory and the processor. So point number 2 is memory is much slower than the processor. Point number 3 is that today, let us, for example, today the real systems where the best of the operating systems are deployed, or the biggest use of the operating system is seen, are today server class machines, for which writing an operating system itself is difficult, and in addition people have to look at lot more of things like the server has to be fault tolerant. Imagine one day morning you log in, your Google Gmail doesn't work. Your system has to be fault tolerant, your system has to be sorry, there is a small disruption here. What did he do? What did he do? Okay, the system has to be fault tolerant. Fault tolerant in other sense, it has to be reliable, and the system also should support something called multitasking. Let us take the Google Gmail server as an example. Millions of users actually log into the system, and it looks like the server is serving every one of them. So you have a sort of a personalized service from the server. So the server should be in a position to handle several tasks at the same time. So because of this, what happens that when I compile a code and I want to run it on a system, I really don't know where this code will be loaded in memory. As of today, what we see is that we are not very, when we compile a code, we really don't know where the code will be loaded into memory. When we looked at the 5-stage pipeline, one of the things we told was fetch an instruction. Fetch an instruction from where? We said there is a program counter which tells the address where the instruction is stored. Similarly, fetch the data from memory. From where? We have an address from which the data should be fetched. So if my program has to execute without any problem, has to execute correctly, you should clearly know where the program is loaded, from where should I get the data, where should I store the data, from where should I get the instructions. So I should really know where my program is loaded. For the program to execute properly, the architecture should essentially know where the program is loaded, where the data is loaded. But if you look at a multitasking system, when you are compiling the code, you really don't know where it is to be loaded. So ultimately when the program is loaded it has to execute correctly. So there needs to be a mechanism wherein the compiler is unaware of the memory location at which the executable code that it generates will be loaded. On the other hand, the hardware should know that. So if I compile a code, what it means to compile a code with this ignorance, and what is it that the hardware needs to support so that it takes care of this ignorance. So that is one very important point that we need to address here. And note that everything is about memory. So what is it that I should build inside architecture, inside your hardware? What is it that I have to give as a facility to the operating system so that what is it that we need to keep inside the hardware? What is it that I need to provide as a facility to the operating system so that this particular or to the compiler so that this particular problem is taken care of. So this is another important thing that we need to handle. So when we go ahead with memory management, we will look at how we handle this particular point number 3. The next point is, whenever you compile a code, do you really know what would be the size of memory? We don't know what would be the size of memory. If we had to know what would be the size of the memory, then probably for every code that we compile, so we will have one compiled version for say 1 megabyte of memory, we will have another compiled version for 500 megabytes of memory, we will have another compiled version for 1 gigabyte of memory, and so on and so forth. So when the code is compiled, the compiler is not aware of what would be the size of the memory on which the program can execute. So the compiler assumes that the entire memory is actually available to this. So when it compiles the code, it assumes, say suppose it is a 32-bit architecture, that means I have 32 bits of address to address the memory, so I can address up to 2 power 32 locations, which is 4 gigabytes. So the compiler assumes that 4 gigabytes of memory is available for it to execute the code. That's the assumption with which the compiler starts. Now the operating system, so when the code starts executing, I hope many of you have compiled a code and executed a code. So you write a program, say hello world.c, you compile it using a compiler, some gcc hello world.c, and you put ./a.out and press and enter. The moment you press and enter, what happens is the operating system needs to allocate space, memory space, to load this program and then tell the CPU, hey, I have loaded this program in this address, go and start executing it. So the first step is that the operating system should allocate space in the memory and see to it that the program and load the program into that memory and then tell the CPU, I have loaded the program at this location in the memory, start executing it. So when it starts allocating the space, please note that the compiler has assumed that the entire address space, say the 4 gigabyte, is available, but you might have a machine which has only 1 gigabyte of memory. So the operating system has a need that it actually opens up 4 gigabyte to the compiler, but it has to manage the execution of this 4 gigabyte of a very less physical memory. So the compiler assumes that there is 4 gigabyte. The operating system should project to the compiler, yes, 4 gigabytes is available to you, but internally it will only have some 1 gigabyte of memory. So that means the operating system is giving to the compiler a virtual memory. Virtual because it is a memory, it is a RAM, it is a physical memory that does not exist, but the operating system will give a view to will give an abstract model to the compiler stating it has that 4 gigabyte of memory. Don't worry. And then the compiler starts using the memory, but then the operating system has to do something to execute that 4 gigabyte of code in a 1 gigabyte of memory. So the operating system projects what we call as virtual memory. To redefine virtual memory, the compiler is given to understand that there is 4 gigabyte of memory available, while there is only less than 4 gigabyte of actual physical memory available. So the operating system has to take care of this illusion that has been provided to the compiler, and it does through a concept called virtual memory, because from the compiler's point of view it is a memory that exists, but physically in reality it doesn't exist, so we call it a virtual memory. Now the hardware has to support the operating system to basically achieve this objective of providing a virtual memory. So that particular support which the hardware does specifically to address the problem of virtual memory is called paging. So in the next three classes, 3 to 4 classes, we will be addressing these 4 points in these 3 points actually in great detail. One thing is that I have a very slow processor, but I have a very fast CPU. How am I going to handle? The second thing is that the compiler is ignorant of the memory location at which the executable code it generates will be loaded, but then the architecture should take care of this ignorance. The third thing is the virtual memory concept which I just explained, and what is the hardware support operating system to achieve this goal of virtual memory. Okay, so these 3 points we will be covering one each classes. Now I will start with point number 1, which is memory is much slower than the processor, and so what do we do to make this match? How do we match the speeds? As I just told you, if I don't match that speed, the CPU will become as slow as memory, and so you don't get the performance. But then how will I match the speed? The instruction that I want to execute, the data that I want for those instructions to execute, all are there in memory. So I have to keep reading and writing from memory. So how do we think that we could go and optimize, or how do we think? So what is the basic way? If at all I am going to go and say improve the performance of the processor, improve the speed of execution of the instructions much faster than the memory access. How I am going to achieve? What is the basic intuition by which I could progress and do something in this issue? So that's the question. Chat. So that's the basic question, and now we will start answering this question in some detail. Will it down? Okay. So somebody has already answered cache. Okay, I'm going to come to that. Good. So the first thing is the basic intuition for improving the processor performance, though the memory is slow, comes from the fact of what we call as this 90-10 rule in software engineering. You will be learning this in a software engineering course if you have one in your syllabus. But what is this 90-10 rule? This says that 90% of your code executes only 10% of your time. That means 10% of your code executes 90% of your time. This is true in many even simple programs like matrix multiplication or matrix addition. Very simple program, very toy programs also. It has a very close look. Maybe it is not 90-10, but it might be some 70-30 or 80-20. But essentially in a very large scale program, this is sort of observed. If you ask me to theoretically prove, we can't prove it, but this is basically an empirical analysis, an experimental analysis, taking wide varieties of program across varieties of fields, varieties of applications, web application, database application, scientific applications, etc. And then you analyze these programs and then come out with this type of figures. So this is an empirically verified fact. So we don't have a theoretical proof for this, but by experimentation these type of statements or facts are basically proposed. Now if 10% of your code executes 90% of your time, that means there is going to be repeated execution of this code. So in a large program there is one small chunk, 10%, which is going to be executed many times. So that essentially means there is, for example, there could be a loop or there could be multiple function calls to the same thing somewhere, but then that is that code which is of very high importance. So if I am going to say take this 10% of code and move it from memory, so in a traditional computer organization there is going to be a random access memory and there is going to be a bus and there is going to be a CPU. This is how the system is organized. Your entire code is in the RAM and it takes lot of time for me to, or very significantly large time for me to move, read and write this memory, because this memory is slow. That's the problem. Suppose this 10% of the code I can push it into some storage inside the CPU, then executing this 10% will become faster, because every time I need not go to the RAM, I can just go to this small storage inside the CPU. It is an high speed storage, the high speed storage. So I can use this high speed storage and I can basically execute this program very fast. This high speed storage is called cache. So this memory, this is random access memory, or we call it as physical random access memory. This cache is called cache memory in some of the books. By putting a local memory, local in the sense it is inside the CPU, it is inside the chip, so it's also called on-chip cache memory. What do you mean by on-chip? It is inside the chip of your CPU. By having this on-chip cache memory, what is the guarantee that your program is going to execute faster? What is the guarantee that this memory being slow, that problem is going to be alleviated? What is the guarantee? The guarantee essentially comes from this fact from software engineering, that 10% of your code executes 90% of your time. And so if I could move that 10% of the code into your high speed storage which is on the CPU, then I am going to execute that faster. So it is a very, very simple idea. So this motivated the need for having a high speed storage inside your CPU. In addition, there was another motivating factor which made, there was another technical factor that made caches possible. Any course in computer organization would not be complete unless we understand this particular law called Moore's law. This was proposed by Gordon Moore, who was one of the co-founders of Intel. What he said was, in say almost a half a century before, what he said was that in every 18 to 27 months your transistor density will double. So what is density? Anything per unit area. So what is transistor density? The number of transistors I can put within an unit area. So let me say this is the unit area. If I can put X today, 18 to 27 months from now on, I can put 2 into X in this place. Another 27 months later, I could put 4 into X. So the amount of transistors I can put within a small, say 1 millimeter cross 1 millimeter area actually started doubling the number of transistors I could put over the years, and it's an exponential growth. So that means that as the years progressed, more and more area in your chip became available for you to go and put more electronics. That also motivated people to basically put more memory inside the chip itself. So large size caches, you can see caches that runs into even now MBs that are inside the chip, that is what we call as on chip. So the Moore's law also motivated designers, architects who are making the CPU systems that yes, you will have enough area to basically look at putting large scale memory even inside the chip. Memory enough to hold at least this 10% of the code, right. So that is another motivating factor for caches to come into existence. Now, we will now talk a little more about behavior of programs, behavior of the executable programs that are compiled, behavior of the programs written by the user that essentially gets compiled and gets executed. These programs follow something called locality of reference. Locality of reference essentially means, so there are two types of locality of reference. One is called spatial locality, another is called temporal locality. What is spatial locality? Spatial locality is that if a particular memory location is accessed at say time t, then the probability that it will be accessed again at time t plus delta t is very high. Let me repeat. If a memory location, say address A is accessed at time t, the probability that a memory location close to it, say A plus some delta x, is accessed at time t plus delta t is very high. Please note it again. I have an address A, say 1000, which I am accessing now. The probability that 1001 says to some 1008, let us say some window, or 999 to some 995, some address in this range, the probability that that address will be accessed in the next few cycles is very high, and that is called spatial locality. The word spatial comes because it is with respect to the address space. Address space is meaning the set of addresses. To repeat, if I access say address 1000 now, in the next few cycles the probability that I will be accessing some address in this range between 995 to 1008 in the next few cycles is very high, and that is the property of spatial locality. On the temporal locality side, if A is accessed at time t, probability that this A will be accessed again at time t plus delta t is very high. I should say probability here. And this is basically called temporal locality. So if I access 1001 once now at this point of time, the probability that again I will access 1000 in the next few cycles is again very high. For example, a very simple example, this comes from the way we code. A very simple example is I initialize a variable and immediately I start using it. For example, A equal to 0, B equal to A plus C, right? So I start using that variable. So I have accessed say location 1000 and immediately I start using that 1000. So within 2 cycles, within the next instruction, I access 1000. So this is an example of temporal locality. An example of spatial locality is, suppose I have a loop for I equal to 0 to 100, AI is equal to, S is equal to S plus AI. Suppose I do. So I access A0, next time accessing A1, next time accessing A2, and note that all these A0, A1, A2 are all, since it is an array, they are all stored in consecutive locations. So I access A0, within the next iteration I access A1. That is an example of what we call as the spatial locality. So this is an example, and here also you can see temporal locality. Every iteration I am accessing S also. So this is an example of both temporal and spatial locality, wherein every cycle I am keep repeatedly accessing S. So if S is stored in say location 1000, so if 1000 is accessed at iteration I access 1000 again in I plus 1. So that is an example of temporal locality, while if I access A0 at iteration 0, I access A1 which is just stored next to it in and the next iteration, then A2 in the next iteration, and so on and so forth. So this particular simple loop can demonstrate both spatial and temporal locality. So this also is taken as an input in the development of a cache architecture. So there are two important things that we need to keep in mind when we are building the cache architecture. The part number one is that 10% of the code is executed 90% of the time, and so it makes sense to move that 10% from the RAM into the cache, and if I do that successfully, then it is going to be very beneficial. It can give us a large performance improvement because it makes the processor almost independent of the memory for majority of the execution of the program. The second thing is that the locality of reference. So keeping this 90-10 rule and also the locality of reference that I have mentioned now, the entire cache architecture is built. So with this I am winding up today. I am opening for question. We have already 8:55. In tomorrow's class I will talk about more on the cache organization. Now I am opening for question. Please hand raise. Chat. It's 2 minutes for them to go down. Okay, if there are no questions, we will meet on next Wednesday. Thank you.